I think it should be recorded now. It should start. Okay, so these are a compilation of practice problems that me and Malhar made. Um, we tried our best to mimic the difficulty of an exam. Even one of them had to be removed. Okay, so it starts with a true or false. Question A. Let F be a maximum flow in a flow network. If we increase all edge capacities by 1, then the maximum flow value in the modified network will be at most the value of the original flow plus 1. True or false? There's one false, there's two false. Okay, false. That's correct. The counterexample is, yeah, the idea of a min cut. So as soon as you have, let's say, something like this, you will increase the max flow by 2 because this will increase capacity by 1, this increases by 1. You can pump 2 more traffic into this flow network. So any flow network that have multiple paths from S to T will increase by more than F plus 1. Is this clear? Yeah. Okay. Next, part B. If F is a flow and we're given some cut S to T, not a particular minimum cut, some cut S to T, and for every edge UV that starts from S and ends at T, FUV is equal to CUV. So all the edges from S to T are saturated. Then we know that S is a minimum cut. Is this true or false? False. 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 Can someone give a counter example? Oh, that's actually kind of hard. Can someone give a high level intuition of what's the extra requirement for us to know that it's a minimum cut? So, um, so we have that all UV edges where U is in S and V in T is saturated. Additionally, we also need VU edges where same thing, U in S and V in T have 0 traffic. So this is the part that's left out. Does a cut have to include either the sink or the source? Yeah, yeah, yes. Okay, this one is actually pretty hard. The next one, part C. There exists a graph where the size of the maximum matching is not equal to the size of the min vertex cover. True or false? Okay. There is, yep, Seems like true is the way to go in here. Can someone give what is wrong, or like why is there such a graph where the max matching is not equal to the min vertex cover? Non-bipartite, exactly. If we give like a very simple example of a triangle, like 3 vertices, it's easy to see that the max matching is 1 as soon as you pick one edge, since you can choose either of the 2 other edges, they share endpoints. But the min vertex cover is 2, because a single vertex or a single node can only cover at most 2 edges, leaving the third edge uncovered. So you would need 2 vertices to become a vertex cover. Okay, we move on. Part D. In any weighted directed graph, running the whole Bellman-Ford algorithm once is sufficient to detect if the graph has any negative cycles. True or false? So once means that it performs the whole algorithm, not just one iteration. There's one true. I see a couple of trues now. Okay, this one is actually false. Yep, false, correct. Because in Bellman-Ford, we have a fixed starting point, right? It will only detect negative cycles that are reachable from the starting node. A weighted directed graph can be connected or it can be disconnected also. So if we consider a disconnected graph, Bellman-Ford can only detect negative cycles that are reachable from the source. Is that clear?
Sorry, can you repeat?
If the graph is disconnected, Bellman-Ford cannot detect the negative cycles that are not reachable from the source.
Okay, thanks.
Yep. Okay. Next one. There exists a maximization problem such that 1, assuming that P is not equal to NP, there is no polynomial time 1 approximate algorithm for the problem. And 2, for any constant epsilon strictly more than 0, there is a polytime 1 plus epsilon approximation algorithm for the problem. True or false? Yes, the answer version will be posted sometime, probably next morning, because I expect some mistakes here and there. And you need to clean those up first. What's the 1 approx algo? Something like your 0, 1 knapsack. So it's not optimal, but it gives you a suboptimal up to 1 range of 1 of like a specific range from the optimal value. Um, yep, 1 approx algo is the optimal solution. That's correct. I think Vassos might have used 1 plus or 1 minus. They're both the same thing. Yep, John, that's correct. This is exactly the 0 knapsack. True. There are NP-hard optimization problems with a polytime approximate solver, like the 0 knapsack, for example. You can give any example in here. Okay. The last one. In a flow network with integer capacities, If the max flow from the source to the sink is unique, then the min cut separating the source and the sink is also unique. True or false? False, yeah. False. Pretty simple. We have S, A, T. This is a min cut. This is also a min cut. Yep, it'll be posted by tomorrow morning on Piazza. Okay. Any questions about the true and false section? If not, then let's move on to the next one. So, question 2. At a bustling convention center, Alice and Bob wish to exchange as many secret messages as possible without reusing the same corridor to avoid detection from Mallory. The convention center is represented as an undirected graph, G equals to VE, where vertices are intersections of corridors and the edges are corridors themselves. Determine the maximum number of ways to get from Alice to Bob within O of mn time before Mallory sniffs out their plans. So your input, once again, is an undirected graph, and your output should be a list of paths from Alice to Bob, where each path is defined to be a sequence of intersections, so like normal paths. Explain the main idea of algorithm, describe the algorithm in pseudocode, and analyze its running time. Okay, before I give you time to think about it, can someone tell me what kind of problem this is? Yep, this is an so yeah, it is a flow. It will solve with flow, but the answer that you need to be looking for, this is the edge disjoint paths problem. But what is different than just using the edge disjoint path algorithm in this case for this question? It's undirected, right? It's undirected, so we can't just use it directly. We need to consider some edge cases. So first, the natural conversion of an undirected graph to a directed graph is that if there is an edge from U to V, this will become like this, right? So replace it with two edges going opposite sides. What's the problem with just running the original edge disjoint paths algorithm on this one? The issue is that you might have some path that uses, let's say, let's call this A. So you might have two paths that use the corridor in the same direction. Yep, that's correct. So you can go like this, and you can go like this. Can someone tell me what is the, or like how should we tackle this situation or avoid it?
In some sense, can we just disregard the center one completely and then do A, U, B and no.
Yeah, that's actually correct. We can completely disregard the middle because if you need to convince yourself this, each time there are paths that use the same corridor in different direction, you can cut out the middle and form a new path that goes A, U, B, and D, V, C. So that's what we'll be using in our algorithm. So we just need to make a simple modification in this case. So this is the path decomposition function, helper function, that the algorithm uses. And we just want to make sure that each time we select the next node, there is no backwards traffic. So the logic in this one is that once we select A, then now we're in U. When we're selecting the next node to go to, we can go to V or we can go to B. But if V has an opposite flow that goes backwards, we avoid it and then we pick B instead. Same goes for this one. If we're in D and we're in V, if we see that going to U means that there's a U to V traffic that goes the opposite direction, let's just go to C instead. So the problematic part in here is that we might use the same edge twice in opposite directions. Our original algorithm treats it as if it's edge disjoint. But if you look at it from the scope of the undirected graph, we're using the same undirected edge twice. Is this clear to everyone? So all we need to do is to add this thing. So this is like, I added this question to mimic kind of like the Bellman-Ford modification problem. This is not an official question. Most likely, if this is like a question in exam, they'll probably give you this thing, then like, let's say, modify it, like the previous Bellman-Ford problem, modify it to work on undirected graphs. Okay, so the runtime is O of Mn, same as the original MaxPaths algorithm. Adding an additional constraint over here wouldn't change anything. Okay. Let's move on to the next problem. So question 3. An array A1 until 2n plus 1 is considered wiggly if your value goes up and down, kind of like A1 is less than A2, A2 is bigger than or equal to A3, and it goes on until the end. So given an unsorted array of called B of real numbers, describe an efficient algorithm that outputs a permutation of A of B such that A is wiggly. So from B, construct a new array A with the same elements as B, but A is now wiggly. So kind of like reorder them to make them wiggly. I'll give you guys 2 minutes to think about it. Think of ways where we can split them to more than or less than efficiently with the algorithms we've learned in the past 12 weeks. Yep, so you just want to make B wiggle. That's right. Does anyone have an idea or an intuition of what values to get from B to make B wiggle? So, what if we first get the median of B with the deselect algorithm, and then from there we can split B into two equal sized, called B low and B high, around the median. Yep, this is an order series problem. And then we can assign the median to be the first value. Then we alternate back and forth, taking it from B high, B low, B high, B low, to make it wiggly until we run out of elements. And doing the median search with deselect takes data and time. So it's good to put the runtimes of deselect and rselect in your cheat sheet. Then partitioning it also takes data n, and constructing the new wiggly A also takes data n. So the whole thing takes data n time. Someone suggested, can we just sort the array? Sorting the array will take n log n time. I think this one should be under data. Yep. Okay. Any questions about this one? Okay. Let's now do the next one. So question 4. You are in your final year of university and are planning your career path. You've heard that job hopping is the best way to navigate the current job market. As a C73 student, you decide to plan this optimally as a weighted directed graph problem. So given a directed edge GVE, each node represents a potential job you could take. Each edge EUV has a weight WE, which represents the probability of getting job V from job U. So this means that WV falls under a range of 0 to 1. You may assume that the graph is acyclic. Your goal is to maximize your career growth by determining the most probable path from your starting job. Let's call this starting job S, to any job by reduction to Dijkstra. So in here, what is the distance function? Distance. Since we're working with probabilities, it will be the product of weight of H1 times weight of H2. Okay. And we're looking to maximize probability. I'll give you guys 4 minutes to think about it first. So this needs to be solved by reduction to Dijkstra. So think of how you would construct a new graph with potentially more nodes, potentially more edges, potentially new weights. Then solving that graph with Dijkstra should give you the answer for the most probable path from your starting job to any job. If you have any questions or you need some hint, please let me know. If not, then let's take this up at 7:15. Let's say you want to land a job at, I don't know, Microsoft. We're looking for the most probable path to get from your starting job at some random company X to Microsoft. What's the best path to get to Microsoft via job hopping? So it's as given. Yes, as is given. So we're looking for the most probable path of job hopping from our given starting job to any position in like the list of target jobs we have, which are the nodes in our graph. Okay, I think Amy has some kind of idea here. Take the complement probability. There's some kind of idea where we need to reverse the probability. But the issue is still one works on multiplication while Dijkstra works on addition. Can someone that perhaps is still pretty good at 831 think of, yep, that is what I was looking for. So we can make use of the property of log. To maximize, so essentially, notice that by logarithmic rules, and because probabilities are strictly within 0 to 1, to maximize the maximum of the product of probabilities is the same as the minimum of the sum of the absolute value of log probabilities. So construct new graph G prime with the same edges and nodes, but replace the edge weight with the absolute value of the log of its original probability. So to convince you guys, log of A, sorry, log okay. Using log, first, log is I forgot the exact mathematical word for it, but mapping from if A is less than B, then log of A is less than log of B. That's one. Probabilities are always between 0 to 1. So if we pick log like ln, like a base that's larger than 1, they would all be negative. Hence, we need to use the absolute values around them. And lastly, logarithmic rules allows us to do multiplication in the kind of like we get multiplication from performing additions. because if we have the edge, or if the path that goes to A, S, A, to B, to C, and this is P1, P2, PT, P3, the probability of this path would be P1 times P2 times P3. But Dijkstra can't multiply. We're not allowed to modify Dijkstra here. We can only feed it a new graph. If we do it as log of P1, log of P2, log of P3, log of P1 plus log of P2 plus log of P3 equals to the log of P1, P2, P3. Is that clear? Yep, you're welcome. So, running time analysis. Let n be the number of nodes, let n be the number of edges. Constructing G prime takes O of n plus n, linear time. You need to scan through the original graph. And running Dijkstra on the new graph G prime, which has the same number of nodes and edges as G, takes O m plus n log n. So it's dominated by this one. So we still need to reverse the weight. You don't have to reverse the weight. You don't have to reverse the weight. Let's say a. So that's actually a pretty good question, Amy. Let's say we have a less than b, where log of a is equal to -3, log of b equals to 2. But if we take absolute relative, the inequality flips. How come this isn't a problem? So the reason why we're allowed to do absolute value in here is that, so let's say we assume that we're using base E, okay? So it's ln. Because probabilities range from 0 to 1, there will always be negative. So the log of P1, the log of P2, they will all be negative. And they will all be negative in the y-axis, yep, when you map it. Yep, the bounds account for it. Brian, is that a question or is that a statement? Question, okay. Because we're looking to maximize AB more than CD, means that he wants to pick AB. We're looking to maximize AB. Give me a second. Okay, so if you can see the part of the log graph that goes below negative, we are flipping it with absolute value, right? So it goes down instead of going up. Yep. Let's not take this. Let's erase this relation. I don't really like it. Like it maps values in a one-to-one manner, basically. That was the point of that statement. we were able to do the flipping and the multiplication by using absolute value of log, and the fact that they're all going to be negative by the upper bound of probabilities. Is this clear? Okay, if you have any questions, we can still pick it up at the end. Okay, question 5. It's now a greedy problem. So Christopher has been tasked with preparing the C73 review seminar, but juggling assignments and other review seminars has left him feeling lazy. Luckily, the AMACSS question bank has questions that cover specific ranges of weeks, making it possible for him to only pick a few questions to efficiently prepare all weeks from week 1 to week 12. Christopher's goal is to select the minimum number of questions from the AMACSS question bank that collectively covers all weeks from 1 to 12, ensuring no week is left uncovered. So an input is a list of questions defined as a closed interval, where questions ij covers week 1 up to week j. And your output is a minimum cardinality list of questions that covers week 1 up to week 12. So explain the main ideas of your greedy algorithm, describe the algorithm in pseudocode, and analyze its running time. I'll give you guys 2 minutes to think about it. If you have any idea or like any high-level intuition, feel free to share it in the chat. Then we can discuss about it. So the question should have been more clear. So we treat weeks discretely. Not continuous. Okay. Someone has some intuition to sort by size. Each question can cover, yep, each question can cover more than 1 week's topic. So let's say we have weeks 1 until 12. If we have a question from week 1 to week 6, then we have a 7, 12. This is considered covering it because we treat it discretely. Can interval be overlap? Yep, they can also overlap. Okay, I see a lot of people that says sorted by the number of weeks it covers, sorted by size. This is yep, Peter got it. It's basically the minimum cardinality cover problem in assignment 1. But instead of covering, let's say, yeah, I just didn't cover in assignment 1. If we sort it by the number of weeks it overlaps, there's actually a possible edge case. It's a counterexample. I should make a good practice and think of a counterexample for that. Yes. Brian has what I was looking for. So let's say we have, for the sake of saving time in drawing, let's say we have 4 weeks to cover. Like 5 weeks to cover. And the question ranges, and we want to sort the question by increasing start week. So the idea is that we want to cover the first week while stretching as far as possible, while still covering the first one. So we will pick this one first. This is the best one, because there's nothing else we've seen before. We'll pick to see the next one. This is the best one. So right now, our current coverage goes up to here. We pick this one. It's not better than the previous option, skip it. Pick this one. It's not better than the previous option, skip it. Once we go to this one, we find that this range of question, or like the range of weeks this question covers, no longer covers the initial week. And we can declare that this one is the best possible option, because any other future or any other questions in this question bank will no longer cover the first one, because it's sorted by increasing start time. Then for the next iteration, so this one is already covered now, covered. Then you move on, focusing from this one, starting from the next question you have in the question bank. Is that clear? So the algorithm looks like this. Sort the list of questions queue by increasing start week. Initialize your initial variables while uncovered, which is like the current uncovered week is less than 12 and queue is not empty. Do question is equal to first question out of queue if start of question is less than uncovered. And end of question is uncovered. So uncovered is covered by this question. Then pop the first question out of queue. So remove it from queue basically. Then if the end of question is better than the end of current best possible question, make that the current best possible question. Else, if we've reached the point where it no longer covers our question, else if start end of question, start and end of question is more than uncovered, that means we've exhausted all the possible questions to cover this week. Add the current to the problem set, then uncovered equals to end of current plus 1. And I think I'm missing another else case. Okay. Cur equals to question. If I is in the for the else case. Is it this else case or is it the second one? Yep. Okay. I'll need to clean up this algorithm a bit more. think it has some missing edge cases, but yeah, that's the idea I want to get across. Any questions about this one? I don't think you would lose much. I'm not saying it just because I made those mistakes. This is the main one that you're looking for. If you've even noticed that sometimes the solutions to the assignments are also missing some edge cases. But like as long as you got the right idea, the overarching idea, you should get the majority of the marks. Okay, you're welcome. So running time, sorting it takes O n log n, iterating through it takes O of n, so it's dominated by the sort, as usual for greedy algorithms, so it takes O of n log n time. Okay. Let's move on to the DP problem. I'll give you guys 7 minutes to read this one and think about it. Then let's take up starting from like high level to the exact answer, how we want to go about it. Okay. Do you guys want more time to think about it, or should we take it up together as a class? Okay. Yeah. Let's take it up together then. So, we are given this n by n checkerboard, and each box in the checkerboard has an integer value score written on each of the square, say wij, for I and j between 1 to n. And we're also given n pebbles. The score of a square only counts when we place a pebble on it, and we wish to maximize the sum of these scores. However, we have some restrictions over here in how we can place the pebbles. So any column can contain either 0 pebble or exactly 1 pebble, not more, while there's no constraint in number of pebbles in the rows. And if any 2 pebbles are placed on neighboring columns, say columns j and j plus 1, with 1 pebble at ij, so let's say there is 1 pebble over here at ij, then the only possible locations for the pebble in the column to the right of it is either at I minus 1 or at I plus 1. Assuming that, of course, these 2 squares are within the board, right? So in other words, if your ij is somewhere here, your I minus 1, you can put it here, or you can, you can't put it outside of the board. There's no more space. And there are also these examples that go through the feasibility of these restrictions. So we want to describe a polynomial time DP algorithm that, given the list of weights W 1 to n, 1 to n, we need to find the maximum possible score for a feasible placement of pebbles. Okay. So the hint, so there's like some kind of idea in here where we have 2 index, right? We have 1 for the row and we have 1 for the column. There are no restrictions for the rows, and based on the restriction for the columns, each column can either have 0 or 1 pebble. And for the second one, it's like what we did just now. The placement of 1 pebble determines the next 2. But at the same time, if we know that the pebble has to be in this box, that means in the previous column, in this column, the pebble is either here or it's here, or there was no pebble at all in that column. It can't be both, because a column can either have 0 or exactly 1 pebble. Is that part clear? So there's some kind of intuition here that it's much better to take up this algorithm column by column, or this DP column by column, and when you're at some column j, you can get relations to j minus 1, based on the second constraint. So let's use the convention of I being 0 to mean that no pebbles is being placed on it, and j equals to 0 means that there are no more columns left to place the pebbles. So for ij between 0 to n, for both, we define the subproblem O of ij for the normal case, when both of them are at least 1. It's the maximum score of feasible placement using the first j columns and placing a pebble on ij. So using the first j columns means that we've scanned through the first j columns. And if I is 0 and j is more than or equal to 1, this is the same like in the example over here. If you notice, we didn't place any pebbles in the third column, but then that gave us the optimal answer. So sometimes the optimum answer means that we don't have to place pebbles because there's also negative values around and have the restriction of if you put a pebble in ij, we're somewhat restricted on where to put the pebble in the next column. So when it's I equals to 0 and j is more than or equal to 1, it means that it's the max score of a feasible placement of using the first j columns and putting no pebbles or no pebble on the column j. And I equals to 0, j equals to 0. That's just the score of leaving the board empty. And I is bigger than or equal to 1 and j is equal to 0. That's the score of trying to place a pebble with no column to place it on. Is the sub problem clear to everyone in terms of how we're going to approach this issue? If you guys want me to go over it again at any point, please let me know. Okay. So now that we've defined our subproblems, we just need to give the recursive formula for it. So let's do it bottom to top. So score of trying to place a pebble with no column to place it on, negative infinity. That's not possible. The score for leaving the board empty, that's like our base case. We have 0. Let's deal with the first one first right now. So we know that in this scenario, we placed a pebble on ij for sure. And we're doing it in a sweeping motion from left to right. So if we know that we have a pebble placed on, let's say this is our ij, what are the 3 possibilities for the column before it? It can, 1, either have a pebble over here, 2, have a pebble over here, or 3, have no pebbles at all, right? So it's the maximum from either not putting a pebble at all in the previous column, putting it at I minus 1, or putting it in I plus 1. The intersection with n in here makes sure that your I minus 1 and I plus 1 is still within the range. And it will be O of kj minus 1. So this is the previous subproblem plus the points that you get, or the weight W of putting the pebble on ij. And for the next subproblem, because we placed no pebbles on the column j, there won't be any plus stuff in here. But in return, we are no longer restricted on where we can put the pebble in the previous column. So it's the max of k between 0 to n of okj minus 1. Is this clear? Or any questions? Is question 6 the hardest? Yeah, it is. It is the hardest problem in the whole practice problem. Can this actually come up? I hope the DP in the final is not this hard. If you can solve this, you can solve any other DP problems. In terms of can this actually come up, I don't think. Maybe. I don't know. I mean, the fact that Vassos didn't say remove it from the practice problems means that it won't actually come up with the same exact one. But in terms of difficulty, I don't know. Haven't seen the paper. Okay. So for the algorithm, we just need to do memoization correctly. And in the end, to solve the original problem, we iterate through each column. So like using the first how many column. Oh, sorry. We made sure we use all the columns in n. Then we iterate through all the possibilities for the last column. Then take the maximum of those. So it starts from 0, where the last column has no pebbles at all. Then from 1 to n, placing pebbles on rows 1 until n, respectively. So that's how to get the final answer. Okay, and the running time. So lines 2, 3, 13, and 16 takes O of n square, because we are working with a 2D array. And it's actually the same as the for loop also. And then is it loop for the 12? There's some mistakes in here. Should be cube. Yeah. So the running time is dominated by the fact that once again we have 2 index and we have to do a maximum in one of the steps. And this one. If you say it's O n cube, it's correct, but you only perform. I think yeah, it's O n cube. Okay. Any questions about this one? I think it should make more sense to you guys once you read the solution slowly again. So the next one is pretty straightforward. So AMACSS is assigning course reps for its courses C, which are divided into 4 levels: A level courses, B level courses, C level courses, D level courses. Each course level has a fixed capacity for the max number of course reps it can accommodate, up to 8 for A level, up to 5 for B level, up to 3 for C level, and up to 1 for D level. Students applying for course rep positions can indicate the maximum number of courses they are willing to represent, R of S, and specify which courses they are interested in, I of S, which is a subset of C. A matching is defined as assigning a student S to a course C. The objective is to assign students to courses such that the capacity limits for each course level are respected. Each course rep's maximum course representation limit is respected. If a course rep S is matched to a course C, then course rep S is interested in course C. So they can only be matched to a course that they're interested in. Give an algorithm that outputs an assignment that maximizes the number of total matchings. And note that if the same student is assigned to 2 courses, this counts as 2 matchings. So, description of flow network. Anyone willing to give the group of nodes that we need to have in between S and T? Okay. Students and courses. So we have, let's see, we have S1, S2, S3, and courses. Let's group them up to A-level courses, B-level courses, C-level courses, D-level courses. What should be the capacity from the source to the students? Yep. R of S1. Just make sure that a student isn't assigned to more than one course. How about edges from students to courses? Should we, yeah, you should only have edges from a student S1 to some course only if they're interested in. What about the capacities in this one? What should be the capacity of the edges? Yep, 1. 1. This is only if student S1 is interested in course and courses A, B, C, D. What should be the capacity of courses from A to T? Yep, basically the constraints over here. 8, 5, 3, 1. And formally, this is what it seems. Any questions about this one? Okay, I think everybody got this one. That's good. So the last question, or actually, so the algorithm to define the desired assignment. So we need to run for Ferguson on F to construct the max flow F. On the exam, if we just draw the flow and write a little bit explaining it, would that be fine? I think it depends on like what you write. If you write the important parts, it will be fine. I think TAs can get a right idea of like sometimes some exams you just have so much time that you should write it down. But if it's like a time crunch, write as much as you can, I would say. So, okay, next. Iterate through all the edges between course wraps and courses. So we iterate over these edges. So these ones. If the edge has traffic of 1 or is saturated, then that is a matching. Then we return the set of matchings. And recall that for Ferguson runs at OM log C. Notice that C is the sum of the capacities of edges out of the source. Let S be the number of applicants and C be the number of courses. We have S plus C, total number of nodes. Additionally, at worst, or like worst case scenario, each course wrap will represent every course. Therefore, C is in O of S times C. Hence, it's the polynomial in the end. Is this clear? Okay. Last question for the day. So, sorry. It is now the 2025-2026 academic year, and AMACSS has revised its course rep assignment policy. Applicants must now submit their transcript, which means for each student S and course C of IFS, so the course that they're interested in, this is in IFS, we have an additional input, T as C, which represents the grade student S achieved in course C. The objective now is to maximize the total sum of grades for the courses that course reps are assigned to. State clearly the role of your variables and the requirements to which each constraint of your LP pertains. And the requirements. The size of your LP should be polynomial to the size of the input, and explain how to obtain the desired assignment from the optimal solution is pretty intuitive in here. Okay. I'll give you guys 2 minutes to think of the LP, and we can take it up together. Okay, shall we take it on together? Yes, okay, let's go. So, this is a 0-1 LP problem. The variables XSC is 1 if student S is assigned to course C, and 0 otherwise, where S is a set of students and C is courses. The constants are like, we can define it to make our constraints become expressed in a more understandable manner. We have cap C, which is the capacity of course C based on its level. So it's this part basically. It's this one. And the objective function is to maximize Z, which is the total sum of grades for assigned courses. So it's the same like the one in your yeah, same thing, dot comma. Yeah. It's the same like what we saw in the past exam paper. So constraints. First one, course capacity constraints. Ensures that the number of course reps assigned to each course does not exceed its capacity. So we iterate through over the students, XC, the sum of it is less than capacity C. Then the same constraints also apply from the student's side. We iterate through all the interested courses and make sure that the sum of it is less than the limit it can represent. Interest constraint. This means that if the student is not interested in that course, C is not in IS, XSC has to be equal to 0, and lastly, the binary constraints. And instructions assignments are binary decisions. Okay, so that's the end for this review seminar. Thank you for staying with me for so long. I will stop the recording now. Oh, shit, stop the there it goes.